In the known universe, there are powerful forces at work with the energy to create and the power to destroy. Over the next hour, we'll look at the largest explosions ever witnessed.
The energy is 2 million times larger than the biggest nuclear weapon ever detonated.
And we'll explore some of the universe's greatest hits.
The energy that was necessary to open this crater is of the order of 10 to 20 megatons.
It's the raw, explosive power of our universe, and you've never seen anything quite like it. $13.7 billion years ago, our universe started with a colossal explosion called the Big Bang. That powerful blast created all the matter in the universe and laid the groundwork for every explosion since. From fiery volcanic blasts to cataclysmic asteroid impacts to exploding stars, nature's most destructive powers were born in that single instant. We'll start with the explosions we know: gunpowder and nuclear detonations. And then take you out into the cosmos to witness explosions of a different magnitude altogether. So what is an explosion? Well, it's energy, a sudden and often violent release of energy. But here on Earth, and in the cosmos, this violent release doesn't have to come from the largest objects. It's often the very small things that create the biggest explosions.
Black powder looks fairly benign, but stored within its molecular bonds is an incredible amount of chemical energy.
Chemical energy is a form of energy that comes from the forces of attraction that hold atoms and other particles together in molecules. In water, for example, hydrogen and oxygen atoms are joined together by strong forces called chemical bonds. When those bonds are broken, chemical energy is released.
It required a lot of chemical energy to create those bonds, and now that we break those bonds, that energy will be released. 2, 3, go! Oh. Boom, that's the way to do it. What we're going to do is take that 250-pound anvil, place it on top of this one, ignite the black powder, and see how high it goes. So it's all wired up, ready to go?
All ready to go.
Okay, Bob. 3.
Fire in the hole.
Fire in the hole, I'm ready. 2, 1. Wow, man. Good job, man, good job. Thank you, thank you.
Setting fire to a few ounces of black powder shot a 250-pound anvil 50 feet into the air. That's an example of the energy set loose when you break a chemical bond. Break a nuclear bond, those bonds that tie the protons and neutrons inside the atom together, and the energy released is enormous. The largest nuclear weapon we've ever detonated had the power of 50 megatons of TNT. Yet the explosions we create are nothing when compared to the raw power of Mother Nature. The 2004 quake in Indonesia that spawned that devastating tsunami had the energy of 100 gigatons of TNT. That's the equivalent of 2,000 of our biggest nuclear bombs. Volcanoes, earthquakes, hurricanes, and tsunamis can wreak havoc over huge areas. But even our mightiest natural disasters on Earth don't have the destructive power of cosmic impacts.
Every 100 million years, everything on Earth that weighs more than 25 kilograms dies. That's more than 50 pounds.
What kills these animals are space rocks, the cosmic leftovers of when our solar system formed nearly 5 billion years ago. Asteroids and hulking balls of ice that are hurtling through space at tens of thousands of miles an hour. And scientists think it was an asteroid the size of Manhattan that wiped out the dinosaurs 65 million years ago.
When the dinosaur-killing meteorite arrived, the energy that the impact brought in is huge in comparison to anything else the human race has done. 2 million times larger than the biggest nuclear weapon ever detonated.
How could an object only 6 miles in diameter wreak such havoc on the entire planet? To understand the devastation of a large meteor impact, let's start smaller, with a rock the size of a house, and the crater it left behind when it slammed into the Arizona desert 50,000 years ago.
This is Meteor Crater. The first time I came to this place, it took my breath away. It's so huge. It gives you just the idea of how much power it takes to form something this big.
Planetary scientist Elisabetta Pirazzo is an expert on the asteroid that left a gaping hole nearly 3/4 of a mile across.
It's astounding to think that a body that is only 150 feet in diameter can create a crater this big.
This meteor was traveling over 26,000 miles an hour. That's 10 times faster than a bullet. When it struck the ground, it gouged out more than 175 million tons of rock and flung it tens of thousands of feet into the atmosphere.
The energy that was necessary to open this crater is of the order of 10 to 20 megatons.
20 megatons. That's 1,000 times more powerful than the atom bomb that devastated Hiroshima. Now, imagine an asteroid 200 times bigger striking Earth, with a blast equal to 100 million megatons. That's what scientists believe killed the dinosaurs 65 million years ago. And it could happen again. So what if it did? What if an asteroid that big headed straight for a city like Las Vegas? The first hint of the impact is a blinding flash. Then the sound.
When an asteroid or a meteor comes into the Earth's atmosphere, it creates an enormous shock wave.
The shock wave, a deafening blast.
You have this thing going at enormous speeds, and you now plunge into the dense atmosphere. It doesn't even have to make it to the ground before you have a huge explosion.
What follows is an apocalypse. As the space rock plunges through the atmosphere, it compresses and heats the air beneath to thousands of degrees. It sends out an air blast at 9,000 miles an hour. The fiery wave incinerates everything within 200 miles. Then there's the impact. In a fraction of a second, the asteroid vaporizes hundreds of millions of tons of rock. The western United States shudders as an earthquake measuring more than 9.7 on the Richter scale levels cities and towns hundreds of miles away from the impact site. As the shaking rages, cities like Denver, San Francisco, and Los Angeles are wiped from the landscape by another wave of superheated rock and debris. When the smoke clears, what's left is a 70-mile-wide crater and a devastated landscape stretching thousands of miles in every direction. The debris that didn't rain down on nearby cities fans across the atmosphere to block out the sun. In the weeks and months that follow, the extinctions begin. Plants are the first to go. Without enough sunlight, they wither and die. Plant-eating animals starve. And after that, one after another, animals farther up the food chain, even us, can't find enough food to keep themselves alive. The devastating energy of cosmic impacts is almost unimaginable. But these impacts shaped our planet in the past and will have dramatic effects on life in the future. If a giant asteroid plowed into our planet, it would have devastating effects. The explosive power of a cosmic impact could be enough to wipe out civilization. But what are the odds we'll get hit by one of these cosmic killers anytime soon?
The question about the odds of getting hit by a meteorite is a difficult one to answer until you say what size meteorite.
Every day, the Earth is pelted with 25 tons of dust and sand-sized particles, but they burn up in our atmosphere. About once a year, an automobile-sized asteroid hits Earth's atmosphere, creates a blazing fireball, but burns up before it touches ground. Every 1,000 years, an object the size of the Statue of Liberty hits Earth and causes significant damage. That's about twice the size of the asteroid that created Arizona's meteor crater. And every few million years, an object as big as a mountain comes along and threatens life on our planet. Government agencies like NASA are hard at work trying to track near-Earth objects. But even if we spotted one of these objects headed our way, is there anything we could do about it? A nuclear bomb might not have enough power to deflect an asteroid. And blowing it up might mean several large meteors hitting Earth instead of just one. But University of Arizona planetary scientist Jay Milosh thinks that if it ever came to saving Earth from just such a catastrophe, our sun might be used to protect us.
Our idea is to collect sunlight with a big parabolic mirror. Focus it down to the asteroid surface. The heat from the sun focuses on the asteroid, heats the surface up to the point where it starts to vaporize, and that expanding vapor forms essentially a crude rocket that pushes the asteroid in the opposite direction.
But is sunlight really powerful enough to deflect an asteroid? Well, at the Sandia National Laboratory in New Mexico, they're already testing to see just how much of a punch concentrated sunlight packs.
We think of the sunlight as a dispersed source of energy. It's not real hot, we can stand out in it. But when we take all these mirrors and focus that light to a point, you get a light that's more intense than anything that we can make with electricity or other power sources.
Chuck Andraka knows concentrated sunlight packs a mighty punch and could be enough to deflect an incoming asteroid. These mirrors focus beams of light to a single point inside the tower with the power equivalent to 7,000 suns. The temperature of these focused beams can reach tens of thousands of degrees.
And that's enough energy in one small place, about that big around, that we can melt anything known to man.
Like a steel plate.
Okay, we're ready. Okay. Oh, we got a nice puddle up here. Still glowing orange, look at that.
Oh, yeah.
When it comes to deflecting massive asteroids on a collision course with Earth, the sun may be our best bet. It is, after all, an object of staggering power that in 1 second creates millions of times more energy than has ever been created on Earth.
The amount of energy the sun produces per second is the equivalent of about 2 billion 100 megaton H-bombs.
Our sun was born some 5 billion years ago, when a colossal cloud of hydrogen began to pool together.
Gravity pulls it together, and it falls together, and it falls together and heats up, and if there's enough of it, it gets hot enough to start nuclear fusion. You'll get to 10 million degrees. At 10 million degrees, it doesn't matter Fahrenheit, Celsius. It's 10 million degrees. It's really hot.
When it gets to a temperature in its core that's sufficient to take hydrogen atoms and stick them together to make helium atoms, the nuclear reaction can turn on.
That nuclear reaction is called fusion. Normally, the positive electric charge of protons at the center of the atom repel one another. But in the core of the sun, where the temperatures and pressures are so immense, they can be stuck together. And when that happens, vast amounts of energy are created. Just a couple hundred years ago, Earth's finest minds thought the sun was a hot lump of coal. Even now, a lot of us think the sun's a solid sphere, burning hot like an ember out in space. But the sun's a very dynamic place, and not at all what we thought of in the past.
The most common misconception about the sun probably is that it's very dependable, so that people just take it for granted. But of course we know the sun changes, and we have to learn about how the sun works because it does affect us on Earth.
If you want to study the sun, this is where you go. Kitt Peak, just outside of Tucson, Arizona.
This is a McMath Pierce solar telescope. It was designed and built in the early 60s. It's still the largest solar telescope in the world.
NASA astrophysicist Don Jennings uses this telescope to study our sun.
The surface of the sun that we see has granulation caused by this turbulence coming up from underneath. And so you have structures that change all the time.
This violent, ever-changing surface hints at the colossal powers at work deep inside the sun.
If you could take the sun and slice it and look at the interior, you would see a very hot core.
The core is the engine of the sun, with a temperature of 27 million degrees Fahrenheit. Gravity is trying to shrink the star, so there's immense pressure at the core, hundreds of billions of times greater than here on Earth. All of the sun's light and energy is born in this nuclear furnace. Here in the center, the pressures are so great and the matter so tightly compact, a particle of light can spend 1,000,000 years trying to find its way out of the core and up to the sun's bubbling surface, where it zooms off into space. 8 minutes later, some of that light hits us here on Earth. The sun's power is vast, and the nuclear process responsible for it not only nourishes Earth, but has the potential to save it from catastrophe. Whether it's powering our homes or running interference on incoming space rocks, the sun is both nurturer and protector. The force of a massive quake. The impact of a giant asteroid. The awesome power of our sun. Each is an epic example of the raw power in the universe. Yet every one of them pales in comparison to the forces unleashed during the explosive death of stars. Once a century, in galaxies the size of our Milky Way, a star blows itself to smithereens in some of the most enormous explosions ever witnessed. They're called supernovas.
By far the most powerful events that occur in the universe today are supernovae. They produce, in a fraction of a second, 300 times as much energy as the sun will produce over its 10 billion year lifetime.
Supernovas only occur in stars that are at least 8 times more massive than our sun. Having exhausted their supply of nuclear fuel, these giant stars undergo a rapid and violent collapse.
The matter of the star, the mass of the star, falls in very rapidly at speeds approaching the speed of light, at which point there's an explosion, which is the supernova explosion, and the material is propelled outward at tremendous speeds.
The flash from a supernova is so bright, it outshines every other star in the galaxy.
We can see supernova in other galaxies for a 2-week period in which the supernova itself outshines the light from all of the stars in the galaxy.
If such an explosion occurred somewhere near Earth, it would be like having another sun in our sky. And if a star any closer than a few hundred light years went supernova, we'd see more than just a light show. The cosmic blast could wreak havoc here on Earth.
The energy released in the supernova could interact with the atmosphere, destroying the ozone layer, stripping the Earth of its protective shield to ultraviolet radiation and cosmic rays. And there could be, in principle, a catastrophic extinction here on Earth.
So is there any chance of this happening? Are there any stars close enough to us that might soon blow themselves to bits and rain destruction down on planet Earth? Thankfully, the answer is no. The closest star that may go supernova is in the Spica system, and it's 260 light years away. far enough where it wouldn't harm life on our planet if it went supernova. Supernovas only happen in huge stars, stars many times more massive than our sun. Yet our sun will one day run out of fuel. And even though it won't explode, the sun's death won't be any less destructive.
Oh, our sun, our poor sun. The sun will eventually run out of hydrogen to burn.
5 billion years from now, the sun will run out of fuel. When that happens, the sun's core will collapse. The immense pressure will force the core's temperature up to 100 million degrees, at which point it begins fusing helium into carbon. The heat radiating out causes the sun's outer layers to swell.
The sun will then go through a phase we call a red giant phase.
It will swell to the point where it swallows Mercury, then swallows Venus, and probably, and it's right about on the edge here, probably swallows the Earth.
Finally, when there's no more helium to fuse, the nuclear furnace shuts off.
The core just locks up and stops, and then the sun is officially dead. It is no longer generating nuclear energy. It is no longer a live star.
Now dead, the swollen outer layers of the sun drift off into space in brilliant curtains of hot, glowing gas.
The outer envelope will just continue to expand and form what we call planetary nebula. That's how a star like our sun recycles a part of what made it up during life back into the universe to form the next generation of stars.
And what's left of our sun is just a small glowing ember of carbon.
It's just gonna collapse down to a hot white cinder called a white dwarf. And this will be a star the mass of the sun and the size of the Earth.
The death of stars are some of the most powerful events in the universe. Whether stars collapse into white dwarfs like our sun, or explode in brilliant supernovae that can be seen clear across the cosmos, they are potent reminders of the powerful forces at work in the universe. The death of stars are some of the most powerful events in our universe. Even on the vast cosmic stage, these explosions are epic events, so enormous, we see their light from billions of light years away. Yet the visible light we see from supernovas are just a small portion of the total energies coming from these enormous blasts. The rest is emitted as radiation our eyes aren't engineered to see. The human eye is tuned into just a very narrow band of the electromagnetic spectrum. In fact, what we can see is just a tiny fraction of all the light on the spectrum.
The only thing that distinguishes one part of the spectrum from the other is the wavelength. They have a different energy, but all of the properties are the same.
If we could turn a dial on our eyes, we could see lower frequency wavelengths, like radio waves, microwaves, and infrared. Turn it up and we could see the higher frequencies, like ultraviolet, X-rays, and gamma rays. And looking at the world in these other frequencies, we see that everything around us emits light.
So a kind of cool thing about matter that people don't necessarily understand is that everything is emitting light. We emit light, you're just not emitting it in the part that our eyes can see. And our bodies are actually warm to the touch, and as a result, they're actually also emitting infrared light.
This camera is showing you my image in infrared. The hot places on my body are giving off infrared, like my throat and my forehead. But my glasses are colder than my body, and they do not give off infrared. They look dark. Hot objects emit a lot of energy. You've got hot water and cold water. You can see the warmer gives off radiation.
More energy means higher frequency, and the highest frequency radiation is something called a gamma ray. Gamma rays are deadly. They pack so much power, they can break molecular bonds.
It can potentially cause cancer in a cell by doing enough damage to the tissue that you've destroyed something.
And when we go looking for this deadly radiation, we see it streaming from the most powerful explosions in the universe, gamma ray bursts.
Gamma ray bursts are the most spectacular events that we know of, and the brightest events in the universe since the Big Bang occurred.
Gamma ray bursts are produced by colossal supernovas. They're billions upon billions of times brighter than our sun. They shine so intensely, they make our sun seem dark by comparison.
To get an idea of how incredibly bright a gamma ray burst is, I'm going to represent the brightness of our sun by this match. And then the gamma ray burst we can represent by the World War II searchlight behind me. It's incredibly bright, but in fact not nearly bright enough. And we would need 1,000,000 trillion such searchlights to accurately represent the gamma ray burst.
These bursts usually come from galaxies billions of light years from our own, so distant that by the time this deadly radiation reaches Earth, it's too weak to do any harm. But if a gamma ray burst were to occur closer to Earth, it would be a different story.
If one of these gamma ray bursts weren't to happen in a distant galaxy, but very nearby in our Milky Way, this could potentially be something that would devastate life on Earth. Some pretty nasty things would happen. We're now no longer talking about just a few gamma rays here and there. We're talking about being bathed in a wash of gamma rays.
If gamma ray radiation from a burst within 6,000 light years hit Earth's atmosphere, it could destroy our protective ozone layer. The ultraviolet radiation from our sun would filter through our atmosphere, killing much of the life on land and near the surface of oceans and lakes. We'd see rapid changes in climate. We'd be bathed in massive amounts of acid rain, and ultimately we'd see mass extinctions in every corner of the globe. So what are the odds of a gamma ray burst happening within a few thousand light years of Earth? Turns out, pretty remote.
Luckily, we believe these gamma ray bursters are quite rare out there in the distant reaches of the universe.
Scientists estimate there's about 0.1% chance of a gamma ray burst occurring in our galaxy. And even then, the explosion would have to happen within 6,000 light years of Earth, which is pretty close, considering our galaxy is 100,000 light years across. The universe is not the serenely beautiful place we see with our eyes. Hidden from our view are powerful forces that reveal ever-present dangers. From supernovas to gamma ray bursts, the universe is above all a place of explosive extremes. There are powerful forces at work in the universe. From man-made explosions to Mother Nature's devastating destruction, to epic blasts of unbelievable cosmic power. All of them reveal a universe of lurking perils, like exploding stars, apocalyptic asteroid impacts, and invisible jets of radiation streaming across the universe. The cosmos is a place of ever-present danger. But what's amazing is that in the entire universe, nothing is more powerful than the colossal explosion that created it all, the Big Bang.
The Big Bang is an amazingly difficult thing to wrap your brain around, which isn't surprising. When you're trying to think about the universe being smaller than the head of a pin,
Actually, smaller than an atom, about as small as the proton at the center of an atom. Whatever the universe was at the very beginning, some 13.7 billion years ago, we think it was tiny, an infinitesimal nugget of space. And then something happened, triggering the most colossal explosion in history. In a billionth of a billionth of a billionth of a second, the universe grew from the size of that tiny point to something billions of miles across. This colossal blast created everything, all the matter we see in the universe today. And it did all this without even making a sound.
When one sees the Big Bang portrayed in a film, there's always a big bang, a noise. Of course, that's silly because sound doesn't propagate in space. But what's often overlooked is that the Big Bang is not just an explosion that happened at some moment in time at some point in space.
it was not just an explosion of material into an empty universe that was sitting there waiting to be filled. It was the explosion of space and time into existence to begin with.
And that's what trips most of us up. Before the Big Bang, there was nothing, literally nothing. And the black void of space is something. So is time.
To ask what's before the Big Bang, what's before there is time, is really a meaningless question. And likewise, to ask where the Big Bang occurred is meaningless because there was no space.
300,000 years after the Big Bang, the first atoms formed. 200 million years later, the first stars are born. And 500 million years later, the first galaxies, including our own Milky Way, begin to form. The Big Bang powered the expansion of space, and all the matter, including every galaxy, got dragged along with it. A balloon works as a good analogy. The surface of the balloon represents the universe. Each red dot on the balloon is a galaxy, and the blowing up of the balloon represents the expansion of the universe. As the universe expands, the space between each galaxy increases, driving them farther and farther apart from one another.
No matter which little dot we sit on, every other dot is running away from us. The farther away we look, the farther dots are running away from us faster. And in fact, there may be some dots that are running away so fast that they go over the edge and we can't see them anymore.
For decades, we've known the universe is growing in size. But scientists had assumed that gravity, the force that attracts and pulls objects toward one another, would eventually stop that expansion and cause the cosmos to fall in on itself in something called the Big Crunch. But then, in 1998, scientists made a shocking discovery.
We discovered that the universe wasn't slowing down, it was speeding up. And at that point, you suddenly realize, gravity doesn't explain this anymore.
But what did explain it? What immense power fuels this accelerated expansion?
We don't have the slightest idea what serves to expand the space between the galaxies. It's one of the great puzzles in modern science.
It flew in the face of everything we knew and understood about nature. So like a sinister villain in a comic book, astronomers gave it the name dark energy.
The whole concept of dark energy is really pretty bizarre, almost flying in the face of physics as we understand it. When we look at the expanding universe, we would expect that gravity would act as a decelerating force to slow that expansion down. However, what we really find when we do a very careful observation is that that expansion is accelerating. It's speeding up. And that result is completely unexpected. It's as bizarre as if suddenly one day gravity just stopped working around us.
Even though scientists are baffled, they know that dark energy makes up 70% of what's out there in the cosmos. So finding the answer to this great mystery has become science's holy grail.
Nothing excites a scientist more than something we don't understand, because that means there's a mystery still left out there to solve. And so, dark energy is sort of the mystery du jour.
Dark energy isn't just mysterious. It's also got a menacing side. If this acceleration continues, some scientists suspect our Milky Way could tear apart. Planets in the solar system would fly away from the sun. And it might get much worse. Everything in the universe could be ripped apart.
If you just expand space-time too quickly, you get dragged along with it. And literally, you could rip apart the planets, you could rip apart the molecules, and even the atoms, until you just get this sort of a uniform sea of the finest paste of subatomic particle that can't get ripped down to anything more fundamental in a universe that just accelerates out beyond imagination.
Fortunately, scientists estimate it would be at least 20 billion years before this apocalyptic end. The enormous power of the Big Bang unleashed forces that nearly 14 billion years later continue to rule the universe. In a single instant, the Big Bang laid the foundation for every explosion since. The universe is a place of frightening power. The energies unleashed on our planet by earthquakes, hurricanes, and volcanoes pale in comparison to the forces at work in our explosive universe. Forces of unbelievable strength and intensity that could, in an instant, extinguish life on our planet. From exploding stars to colliding asteroids, we're at the mercy of immense powers we only barely understand.